this assessment asks us to show the mechanism of the proline catalyzed aldol reaction. This reaction is an example of organocatalysis. Organocatalysis is a field that recently won the Nobel Prize in Chemistry, so this is a really cool reaction. As we do with all mechanism problems, I've gone ahead and numbered the carbons 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. The assessment gives us a hint that we should use the proline to make an enamine and then regenerate the proline later on. Because enamine formation is not the subject of the main topic of this chapter, and because I want to keep this video to a reasonable length, I've gone ahead and shown how our secondary amine in proline would react with the ketone to give us this enamine. So you can fill in those mechanistic details, but we're going to start with this enamine. Now, having made the enamine, we know that enamines are nucleophilic at carbon 3, and aldehydes are electrophilic at carbon. So we now have a nucleophilic 3 and an electrophilic 4 to make us this needed 3-4 bond. And so let's show how that happens. It's going to start with the lone pair of electrons on nitrogen collapsing down and pushing the pi electrons to attack carbon 4. The CO pi bond is going to break with the electrons moving on to the oxygen. That will give us the following product. Now, we don't usually see enamines reacting with aldehydes, but they do in this particular case. There is usually a single stereoisomer produced in this reaction. We won't worry about why that is now. We'll talk about it at the end, even though it is one of the things that makes this such a cool reaction. So we'll go ahead and show this stereochemistry, this O- on a bold wedge. Let's put our numbers back in to confirm that we have in fact formed the 3-4 bond. Now, having done this, what's next? Well, we need to protonate this oxygen to give us the alcohol, and then we need to hydrolyze this iminium back to the ketone. And so we can do that in the same way we would have done in previous chapters. We can use this O- to grab a proton. There's probably some water in solution at this point, so we can simply protonate that alkoxide using water, and that's going to give us this. So we've made the hydroxyl group, but we still have the iminium. Now, this iminium can be hydrolyzed to the ketone using water by a mechanism that, again, is not the main topic of this chapter. So just to keep the video short, we'll just show that this iminium reacts with water to give us the ketone. This is the mechanism of this reaction. Now, what is it that makes this such a cool reaction? What makes this a cool reaction is that we're able to make molecules that are enantiomer enriched. So in this case, up to 76% EE, favoring only the molecule with the hydroxyl group coming towards you. That was a big step to be able to take organocatalysis and use it to make molecules that are single stereoisomers or at least enantiomer enriched. Why is that? Well, this proline gives a chiral environment for that reaction to happen in. And so when this reaction is conducted in the presence of a chiral environment, proline itself, we get that enantiomer enrichment. So that certainly contributed to why organocatalysis won the Nobel Prize, but not exactly pertinent to the mechanism on the screen.